Hey everyone, I'm Kobee, and in this video for COT 5405 at UCF, I'll be proving the lower bound of the element distinctness problem. So the problem goes as follows. Given an array of n elements, we want to determine whether all the elements are unique. So if we look through the array, find no repeated elements, we could return true or yes, and if we do, we'd return false or no. So just looking at these examples here, one simple approach that is really stupid and naive, but one that humans would come up with immediately is to just scan all the pairs in the array. So we just check the 21 and 98 with the 76, on and on until the end of the array. If we don't see it anywhere else, then we know that one's safe. Do the same for the second index, and then we repeat this process until we reach the last one. And the problem with this is that it's really slow because we are exhaustively checking every possible pair of elements in the array. So that gives us an O of n squared runtime, and we can do better than that. So a slightly better approach is to just sort the arrays and check the consecutive pairs to see if those are equal as we walk through them. So for example, in A1, if we were to sort that, we'd have -7, then a 21, then a 43, then a 76, and 98. So walking through this pair by pair, we check this pair, those aren't equal, this pair is also not equal, and not equal. So we've reached the end of the array and had no equal pairs, so we can safely say that yes, every element in here is distinct. Now if we ran the same thing on A2, we'd first sort it, so we'd see -42 first, -3, -3, 11, and 39. Now doing the same thing, checking this pair, it's not equal. This pair is equal, so if you were coding this up, we just return right here and say that no, there's a repeated element and not all the elements are distinct. So this approach runs in O of n log n time, as you might know, because first for sorting, we take n log n time as that's the runtime for any optimal comparison-based sort. And then we do incur these n steps of work later on just to compare the pairs, but that's obviously overshadowed by the n log n. So the question is, can we do better than this? Technically, yes. If we were allowed to hash, which we, in other circumstances we could just throw all the elements into a set as we walk through the array, and whenever we see an element, we could see if it's in a set. If it is, then obviously we have a repeated element. If not, then we keep going. But the problem is we have this restriction on our model here, and that is that we can only compare elements to other elements. So, using less than, equal to, or greater than. And the problem with hashing is obviously you need to know the true value of the element to hash it. You need to perform some arithmetic on it, which this model doesn't allow for. So our problem here is to prove whether we can, with this restriction, can we get better than O of n log n times, so little O of n log n, maybe with some other approach that doesn't rely on sorting. And the answer to that question is no, which is what we're going to be proving in this video. So the first thing that we're going to talk about that's related to the proof is a decision tree. And a decision tree, at least in the case of sorting, you can think of as like if you were to hard code a sorting algorithm for an array of some fixed size. In this case, we have an array of size 3. This is basically what your program would do under the hood. So basically, in this decision tree, each node is going to correspond to some indices of the array that you're comparing, and the edges are going to be the results of that comparison. So in this case, if we compare the first and second elements, if the first was less than the second, we'd go left. If it was greater, we'd go right. And these leaves, which aren't circled, are basically the results, or the correct permutation of the indices such that the array would be sorted. So if we were to walk through an example here, 19, 42, and 7, I've labeled the indices there. So first we compare the first and second elements. 19 and 42, 19 is less than 42, so we take the left branch. Compare the second and third elements. 42 is greater than 7, so we go right. Now between the first and third elements, 19 is also greater than 7, so we go right again. And so this right here is the ordering of the indices to make the array sorted. So if we were to just map that out down here, the third element should come first, so 7 comes first. The first element should come second, so 19 is there, and then the second element should come third. And as you can tell, this array is sorted. And now, one thing I want to point out is that for an array of size 3, we have 6 or n factorial or 6 possible permutations. Now, of course, only one of those will be a correct sorted array, but we still have that many possible ways to arrange the elements. So here, n was 3. We had n factorial possible options for arranging the array. And one thing to note is that if we were to determine the height of the tree, of a binary tree, it's basically just log base 2 of the number of leaves. In this case, you'll notice that n factorial, or 6, is actually the number of leaves we have here. So writing that like this, we also know that this simplifies, or is actually in O of n log n. Now as for y, I'll do that over here. If you were to expand out the n factorial in the log, you'd have log of n times n minus 1, all the way down until you multiply by 1. Now you can expand this out with log rules because the product of these elements will just, expand out to the sum. So you'd have log of n plus log of n minus 1 plus all the way down to log of 1. Now writing this as a sum, we'd have this. So the sum from I equals 1 to n of log I. And we also know that this sum is actually bounded by another sum, which would be the sum from I equals 1 to n of log n, right? This is just log n added to itself n times, which is just n log n. And that's how we know that this function right here, log of n factorial, is actually in O of n log n. And so the cool thing about this is it tells us on average how many comparisons we need. This tells us the height of the tree, which corresponds to the number of comparisons we need to determine what the sorted array is. And that gives us a nice bound for our problem. So you might be wondering whether we can just apply that same decision tree model right out of the box to our element distinctness problem, because what we covered previously was sorting. And the answer is somewhat, just we'd have to make some modifications. So something about this tree is that we had a single leaf for each possible answer that we could have spit out. So these are all, of course, possible permutations of the input array. And so if you were to apply that same principle to the element distinctness problem, it wouldn't really work out well because we have only two possible answers, right? We have yes or no. Yes, that all the elements are distinct, or no, that there's a repeated one. And of course, log base 2 of just 2 is 1. And so we know even just from looking at the example problems that we need, for any possible input size, we need possibly more than one comparison to determine whether all the elements are unique. In fact, this would only apply if our array was of size 2. So yeah, this isn't very helpful. So we're going to need a different approach and a different, a modified version of this tree to suit our problem. So in our new decision tree, we'll have the same components, of course. We'd still have a node that will compare elements of the array. We'd still have branches off those nodes. But something different about the branches this time is that for the element distinctness problem, we actually care whether the elements we're comparing are equal, because of course that would require us to branch to a no answer. So what we're going to do is a little bit different, because for algebraic decision trees, they should all be binary, which means they should have only two edges or two children at most. So we can't have a third branch for the equal. So what we're going to do instead is have like a kind of compound branch. So we'd have a less than or equal comparison, maybe a greater one over there. Then down here, we can have a separate comparison over here for determining whether it's actually, whether I is less than j or whether it's equal to. And of course, if it's equal, we'd just, return no. If not, we can keep going. And then eventually, in the cases where they aren't equal, they'd eventually bubble down to a yes answer somewhere. Same deal over here. So yeah, that's what our new decision tree would look like. And what we want to show is that, as we saw in the case earlier, we want to know whether the number of yes leaves is equal to n factorial, because of course, as we discussed earlier, log base 2 of n factorial is in O of n log n. And that's kind of the bound that we want to prove. So what we're going to do is a pretty powerful technique for proving lower bounds, which is a proof by transformation and reduction. So the basic steps are that you first transform your problem into another type of problem or into some other domain. Then you'll solve the problem in that domain and transform the solution back so that you can solve the original problem. So note that our original claim, I'll write it here, is that this decision tree should have at least, so it should have greater than or equal to n factorial yes leaves. And we don't really care about the no leaves right now. We just want to know, whether they're all distinct anyway, so we care about the yes leaves. And so how we're going to transform it is basically we're going to treat all of the inputs as if they were coordinate points in n-dimensional Euclidean space. So for example, if I had an input of size 2, let's say my array was, I don't know, 3, 3. How you think about this from now on is as a point that's just 3, 3. So if you were to draw this out on a grid, this is what it would look like. You'd have one axis here, another axis here. So say this is the x-axis, this is the y-axis, and these correspond to the indices of the input. So x would be the first, y would be the second. Now, there's going to be a region here, of course, but say you just plot this point 3, 3. That would be, I don't know, somewhere over here, I guess. I don't really have bounds for these, but pretend it's over there. And that gives you that point in Euclidean space. And so one neat property of doing things like this is that you can kind of define a region for your work. So say I was just concerned with the positive real number space. I'd have like a region like this. And all of my inputs that I could feed into this decision tree would kind of fit in this region. Pretend that that's not 3 right now, by the way. Pretend it's just infinite. So yeah, you could pick any two elements as your array indices. You'd plot them in here, and then you'd have some points. Now the cool thing to note is that whenever x and y are equal, remember if x and y are equal, that means that we have a duplicate. So whenever x and y are equal, that's basically just this line, right? This line y equals x, which bisects our region in two pieces. So if any point is on this line, we know it's going to end up in a no leaf. Whereas if it's on this top left half or this bottom right half, eventually that point will find a yes leaf. Now, of course, which leaf it reaches depends entirely on which side of the line our point is. So if it's on this side, in this case, x would be greater than y. So we'd follow in our decision tree. We'd see that I is greater than j. We'd go over here and we reach a leaf over here. If it was on this half, then y would be greater than x, and we'd instead go left. So we'd reach another yes leaf over here. So we still reach a yes leaf, but it'll be a distinct one, depending on which side we're on. But yeah, so representing our problem like this also lets us do something else, which is think of it like we are splitting our region into separate chunks or connected components. And you'll notice that the number of connected components will match the number of yes leaves. And so what that allows us to do is kind of transform our original claim that the number of yes leaves should be greater than or equal to n factorial into us trying to prove that the number of connecting components, let's say that W is the set of all connecting components, and we want to show that the number of these should be at least n factorial. And so yeah, going on, we'll be proving this, and once we prove this, we can kind of transfer our logic back to prove our original claim. And just for clarity, a connecting component, it sounds exactly how it is. It's basically just a component that is connected. So mathematically, the formal definition is that it's a region where you can have a path between any 2 points in that region that only goes through the region. So if I was in this top region, I could have some weird squiggly path that reaches this other point, and this path stays entirely within that region. It does not leave. So this is connected. Likewise, on here, it's also connected. But since connected components are kind of very, very flexible and loosely defined, we're going to be instead focusing on convex components. So basically, the only difference between convex and connected is that if a region is convex, you can draw a straight line between any 2 points that does not leave that region. So if I were to do a more complex example, say you had a, I don't know, say you had this cashew-shaped region. This is convex, this is connected because you can draw a path between these 2 points without leaving it. But say I wanted to draw a straight line between this point and this point. That line would obviously leave the region, so it's not convex. It's connected but not convex. But this also means that any region that is convex will also be connected. So that's what we're going to be using moving on. We're going to be showing that, we want to know how many connected components there are, and that it's greater than n factorial, and we'll use this concept of convex and connected to kind of later on contradict one of our future claims. So now let's get on with the actual proof. So remember, currently we're going to be proving this subclaim, which we'll use the proof of to prove the original claim. So yeah, anyway, we're going to stick to 2D for this. So imagine you have a input of size 2, like 3, 6. This would, as we discussed earlier, this would go into, since the jth component is larger than the ith component, that would essentially mean the y-axis, it would be higher on the y-axis than the x. So this point would fall into this region over here, into this connecting component. Whereas if the opposite were true, if say we permuted this to become 6, 3, now this is the ith and this is the jth, so this point should fall over here in this bottom component. So intuitively, as we thought about it earlier, what we're essentially saying is that for each unique permutation of the input, you'd need a separate component, right? Because as you go through the decision tree, they'd essentially, reach distinct leaves. That's what we want to prove. But in order to prove this, let's try claiming the opposite. Let's assume for a second that these two distinct permutations can actually reach the same connecting component. That means we don't actually need a separate component to handle both these cases. So let's call that P. Let's say P is 3, 6, and P prime, which is a unique permutation of P. Let's say that's 6, 3. So yeah, what we're saying is that we can essentially squish both P and P prime into the same component without issues, without any problems. So P would be here, maybe P prime would be here. This isn't accurate, by the way. I'm just putting them in there arbitrarily. But anyway, so we know this region we're in is convex, and by splitting it along this, remember this line was the line caused by the no leaves. By splitting a convex region linearly, so either with a line or a plane, the two resultant regions would also be convex. And since they're convex, we know by definition of convexity that you can draw a straight line between any 2 points in that region. So let's draw a straight line between P and P prime. So essentially what we've done is taken P, and we now know that there's a set of points along this line that are also in the region, and those points lie between P and P prime. And now something interesting happens here. So I want you to take a look at P and P prime for a sec. So with the indices here, I and j, we see that P sub I is actually less than P sub j, right? 3 is less than 6. Which means that P sub I minus P sub j should be less than 0. A small number minus a larger one is a negative number. Now if we take a look at P prime sub I is greater than P prime sub j, 6 greater than 3. So if you do the same thing, we find that P prime sub I minus P prime sub j is actually going to be greater than 0. And so this is peculiar because let's take a look at the line between them. If you wanted to model this line as like an equation, you'd have z. This isn't really necessary, but in case you were curious, you'd have some constant, some coefficient lambda times p plus 1 minus that coefficient lambda times p prime. And so this essentially is a model of every single point between p and p prime. You can vary lambda and get any point in here. So, for example, the midpoint of p and p prime would be at 0.5p plus 0.5 p prime. And so where we're going with this is that what we're trying to say is that this sign changes at some point along this line. Right? To get from a negative part of the number line to the positive part of the number line, you have to cross over 0. And so what that means is that this line z, so at some point, z sub I minus z sub j has to equal 0. And that means if you move the z sub j over to the other side, you see that z sub I equals z sub j. And this right here is a big red flag because we've just contradicted ourselves. So remember that this no line in the middle that bisected our region is actually meant for the cases where the ith component equals the jth component. But here, since we know this region is convex, this component, and that this line should actually be within that convex region, this yes region, we're saying that we have a point where the two elements are equal within one of these yes leaves, which is a contradiction. So what that means is that our original assumption was false. We can't actually assume that we can put these two unique permutations within the same leaf, and thus they need separate leaves. So what that boils down to is that for an input of size n, we have n factorial permutations, right? So what we've proven now is that each of these permutations, since these are how many distinct permutations we have, each of them deserves their own connected component, and by extension, with our original claim, they thus need their own distinct leaves. So two such inputs, two such permuted inputs can't actually end up in the same leaf. Of course, this isn't constricted to like input itself. So for example, if you had the case where this was your point, 8, 10, and 3, 6 would still be in the same leaf, of course, because their relative ordering is the same. But if you were to permute them, then they'd need different leaves. So that's what we're saying here. So we need n factorial different connected components, and thus n factorial different leaves. And if you remember from what we started with, we know that log base 2 of n factorial is in n log n. Specifically, we're saying that the bound should be omega of n log n. So that's pretty much what we've proven, that we need at least this many comparisons. That means our tree should be this high. This should be the height of our tree, in the worst case, of course. So that's how many leaves we need, that's how high our tree is, and that's also thus essentially the runtime of the best algorithm we can design for this problem. So that concludes our proof, but just to convince you, since we've done all this in 2D, that it also works in higher dimensions and for other inputs, I'd like to quickly show you the same process that we just walked through with the bisecting everything, just in 3D. So if I go here, all right, so first we're going to start off by just showing the plane x equals y. So if I run this, you should see, here's our cubic region. We have our first kind of bisecting plane, which gives us two connected components. Now if we run with the plane y equals z, we should see some more splits. So now we have, if I can get a good angle, yeah, so now we should have 1, 2, 3, 4 regions. These are all disjoint connected components. And then if we run again with the plane x equals z, we should see that now we have 6. So yep, 1, 2, 3, 4, 5, 6. And that lines up with our prediction that there should be n factorial connected components, which means there should be about n factorial or more leaves. Yes leaves, that is. But anyway, I hope this was all informative and clear to follow. If not, feel free to leave some feedback in my peer review or in the comment section below. Thanks.